Hello and good day to you. So today I'm showing off my genetic algorithm. Slightly confusingly, there's a castle on the screen and the dragon is firing fireballs at the castle. But what the dragon and the castle are just two different locations, and it's the fireballs themselves which are the genetic algorithm. They're the bit that are trying to learn how to hit this castle, and they learn to hit this castle as a population. They don't behave as individuals. So what happens is you have a class called Cannonball, and that holds the angle, which is its physics of going upwards, which is counterbalanced by the weight. So over time, the weight will reduce down the angle value until it becomes a negative number and it plummets to the ground. Similar thing going on with the force, which is the moving along the x-axis. So, and this is counterbalanced by friction, which will slow it down until it's quite at zero and not going forward anymore. It also has a timer set for the number of frames that it can exist in the world, and when it hits zero it stops moving and it's finished. Now the aim of all these cannonballs / fireballs is to hit this tower. If I rerun the program, you'll notice that they start off really badly, and that's because they start off completely randomly. And what they do is each generation, and as in you just saw one generation, they recombine their values, tending to choose the better values amongst themselves to produce better cannonballs or fireballs the next time. So as you can see here, they're just slowly reducing down their values, and this number being printed out to the console is the average distance of the population to the castle. So you can see over time the population is getting a bit better at moving towards the castle, and it will keep on running until they get really they'll get really synced up on hitting the castle. And they do this by every time it runs out of fireballs. It has two functions in this sort of class that's acting as a bit of a database for what the fireballs are doing. It has mainly two functions. One is to update the screen and check what's happening to the fireballs, and either say yes, I'm ready to move on to the next iteration or not. And you have an evolve function which uses roulette wheel evolution. So this is something I found fascinating with genetic algorithms. They're not very good if you choose the best and brightest only. They're really good if you choose a weighted tendency towards the best and brightest, and that might sound like hair splitting, but you've got to think of it like this: that when I haven't done this, when I have set it up so you can see there's a massive improvement even just while I'm talking. If you only choose the best fireball and you replace all the weak fireballs with the best fireball, this doesn't happen. It doesn't improve. What it does is it converges very quickly on a very limited set of outcomes, and it will sort of go, well, this one's the best, and I'll stick to that method, and it won't try the other search space within the data. Though the solution to that is like a roulette wheel. So all of these fireballs being flung out have a chance of being recombined into the next population. But the ones that are closest have the biggest chance Now, what's interesting is if the chance of the closest, the best being being in the next population and replacing all the next values is too high, you break the algorithm again. It needs to be kind of this combination of democratic and elitist, as in I can't quite explain it properly, but the first time I did this, I actually tried to use the distance itself as the fitness value. So the least closest would have really low chance of being used as the data for the next population, while the closest had almost overwhelming chance. And it actually went in the opposite direction and just completely broke. Where it works is where if there is just a slight chance of the worst performing being not used to form the next generation, and the best performing to being used, it has a tendency towards continuous improvement. And what I notice is you get this nice sort of population distribution, and it feels like to me mathematically what happens is this population communicates with itself to retune the whole population. So that one that's gone completely off is very unlikely to be recombined each time, but you can see that it survived a couple of generations, and it was in there. It was still supplying some information. If you don't do it like that, it doesn't seem to work. Now, what is this really useful in terms of actual practical applications? Well, you have lots of algorithms that you use, and a lot of them need a lot of high parameters and tuning. And I guess the interesting thing about genetic algorithms is you can write, if you've got a fitness function, and the fitness function is how close am I to the castle when my fireball finishes. You can work back from that, rank your values, use it to train other algorithms, and it's useful. I think if you've not encountered the idea before, it's probably a bit as if I'm talking absolute nonsense. But you can see that there's a quite nice little mathematical convergence there. It finds, a solution, and it's based on genetics and Darwinism. I liked it. Have a good day. Thanks. Bye.